Okay, so let's just quickly recall where we are. So we looked at first standard LDBC code, regular case, and we looked roughly how we can analyze them, and we saw these exit curves, and then we saw that if I kept the rate fixed, but I would keep the degrees going up, then unfortunately the achievable threshold would go to 0. And then we looked at the construction of the spatially coupled, and we saw that at least something interesting is happening, because even though locally they have exactly the same degree distribution, and even if we let the degrees go to infinity, their threshold will stay bounded away from 0. Now that's of course not enough. If you just want something that's bounded away from 0, there are many other ways of doing it. What we want to show is that they're very good and indeed achieve capacity, right? But at least we saw that there's something interesting going on. So now how would we, for spatially coupled, how would we analyze this? Again, just a binary ratio channel, right? We will do exactly the same thing that we talked about before, right? Before we had on this board these recursions, epsilon, there's an epsilon received, the message is coming in, the message is going out. And so this is exactly the same. So let's assume this is now my spatially coupled structure. So this is kind of the protograph picture here. So here I have my variable nodes, here I have my check nodes, and this is again the 3-6 picture, so I have always 2 variable nodes per check node. And so now let's assume I wanted to do exactly the same analysis. Well, again, if this was the protograph, right, then each of them would be connected, maybe one here, maybe one here, maybe one here, and so on. And so again, I would have to write down these dense evolution equations, but there's now one crucial difference, right? In the random structure that I have in the code, there was, this was completely amorphous. There was no structure in the code. This was random, okay? All I had is every variable node looked the same than every other variable node, and they had, with high probability, this support tree. So I didn't have to make any distinction between variable nodes. But now I have this spatial structure, and in particular, the spatial structure at the boundary, the symmetry is broken, right? So it's not just this circle that we had before. So now it's not clear, and indeed it's not true, that this node here will behave the same thing as the node here that I have at the boundary. And so because of that, when I write now these equations, I have to write down the recursions in which they have these erasure probabilities, but at every position, it might be a different erasure probability, right? Within each position, they all look the same. But at different positions, they can be different. And so what happens is at the boundary, remember I had these variable nodes that are fixed, okay? So these are perfectly known, so I have perfectly known information. There are some boundary nodes like this, but inside here I have some x, and so now I have an xi that I have to deal with, okay? So these equations look exactly the same as before, but except that now this x not just have an index in general, which I didn't write here, which is the number of iteration here, so x of L, but it also depends on the position I'm looking at, right? So xi now is the same equation I had before, but now what I'm seeing here, the incoming things that I'm seeing, they are not all the same. It's not just a y, but it's actually an average over y's over different positions. Okay? And so what this average here is, this depends now a little bit if I'm looking at the protograph construction or if I'm looking at the random construction. This is now for the random construction. So the important thing is that you simply see that now it's a coupled recursions that formerly look the same, but now I have averages of these quantities and I have indices for each position. Okay, so I have now a whole vector x and a whole vector y, whereas before I had only scalars. But other than that, it's the same, right? So, okay, so I can do that. So this is now the recursion that I have, okay? It just looks, it's exactly the same I had before and here, except now I have one for each xi, and each of them now I have averages, okay? These sums are new. And the sums go over the window, whatever window I choose things to spread out. Okay, so there's now different forms, depending if I do it exactly one to each position, if I spread them out, the window might have weights. This depends on the construction. Okay, so now if I simply run these recursions, this is exactly the equivalent of what I did before. And so rather than, right now, going through the equations, let me just show what now the result is. Okay, so what is now the experiment? I take this spatially coupled construction, okay, maybe something like a 3-6 ensemble. And now what I do is I'm initiating with a certain epsilon, and the epsilon will be here below. Okay, and I run this experiment for different epsilon values. And now I simply show you the value of these xi's at the various iterations. Okay, initially the value is 1. Okay, so these are the exit values. Initially there's nothing that's null. And now hopefully these values will go down, right, as a function of the iteration. Now what I have here is a fairly long structure. So this is a structure of length 100. So I have 100 copies here, just so that we see things, right? And so now, unfortunately, I apologize again, you can only see this the top here because these things you can see. The height of the bar is exactly x, okay, at position I. So at position 50, the height of this bar will tell you what the erasure probability at a certain iteration is, right? And so now you will see that these x's will not all be the same. They might differ. So let's run the experiment. Okay, so we run it now, and the epsilon we run it is an epsilon that's below the BP threshold of the code of the uncoupled one. So that should be easy, right? So for example, for the 3.6 code, the BP threshold was 43%. So maybe we run it here at 40%, okay, with only 40% erasures. Now, clearly this should be able to do it, right? Because it has a little bit help at the boundary, but already without the boundary help, it should be able to do it. So let's do it, right? Let's run. So you see it goes down. And you can see that essentially, if you look at the middle, there's at the boundary a little bit something happening, okay, but not much. Okay, why is it a little bit better at the boundary? Because at the boundary I have extra information. I have some bits that are set to 0. These are known values. But essentially, let's run this one more time. If you look at what these values here, these values would be exactly the same, the values that you would see for an uncoupled system. Okay, so the values in the middle are exactly the same values and iterations that you would see if the system was not coupled. So nothing really super interesting happening here, right? But now what happens now if I'm fixing the epsilon and go beyond this threshold, right? So before, 43% was the threshold. Now what is if I try, let's say, 47%, right? What would happen? If I tried this for the uncoupled system, it would simply get stuck in a fixed point, we have seen, right? So let's see what happens. Okay, so you can see this gets stuck. And this is exactly a fixed point you would get stuck with a single system. But something interesting happens, right? At the boundary, because at the boundary it's better, it actually can start decoding. And you should really think of a wave, think of a continuous wave. And this wave moves in at constant speed towards the boundary. And since I have two boundaries in this case, it moves in from both sides. Okay? And so it will simply go. So let's maybe play this one more time. So as you can see, it starts decoding. In the middle, indeed gets stuck. Exactly the same behavior as the uncoupled system. At the boundary, since I have help at the boundary, it actually starts decoding. And think of this as a continuous wave which goes at constant speed towards the boundary. And anytime something gets decoded, okay, this helps now the next neighbor, and then this gets decoded, helps the neighbor. And so I'm going from the boundary slowly towards the middle until I've decoded everything. Okay? And this goes up to a certain value. And indeed, okay, so I'm not giving much away. Typically it's called the area threshold, but it will turn out that it's exactly the map threshold of the underlying ensemble. So this goes up to some value. If I go up beyond this map threshold, okay, so it turns out that the map threshold of the uncoupled and the map threshold of the coupled system are essentially the same. And so if I go, of course, beyond it, then what will happen is, then if I go beyond it, then of course eventually I will just get stuck, right? Now, even a map decoder could not decode beyond that, right? So that's beyond. The map threshold is the threshold that an optimum decoder could achieve. Okay, so below the uncoupled threshold, it behaves essentially the same as the uncoupled system. Above the map threshold, where the map threshold is the same for the coupled and uncoupled one, okay, it gets stuck. Not surprising. The interesting thing is in between. Between the BP and the map threshold, it actually behaves very different, and these thresholds can be quite different. So, for example, for the 3.6 code, for the 43% now goes up to 48.84 or something. Okay, so the map threshold, if you could decode the 3.6 code map decoding for the BC, it has a much better threshold, and this code will actually achieve. Okay, so now, okay, this is a slight mistake. So the question is essentially, up to which threshold does this thing go, and why does it go? Okay, so typically this is called the area threshold, and I'll tell you in a second why this is called the area threshold. But as a summary already, this threshold, this area threshold, and which is called like this because it's defined in one way to characterize this in terms of an area, which I'll show you in a second, turns out to be equal to the map threshold. And one side effect of this whole analysis was actually that we now know for this code, for these LDBC codes, we can also determine what their map threshold is. So in general, if a few years ago you would have asked, let's say I take a 3.6 code, I have a Gaussian channel. Let's assume I could do map decoding. What would be its threshold? Turns out that that's actually a very difficult problem. okay? But it turns out that actually via this detour, okay, we can determine now what the threshold is, and it's exactly the threshold of this coupled system. And you can put numerical values to this threshold. Okay. Now, let's go back to the physics interpretation we had in the beginning, and just to see another instance of this nucleation process. And this is another story very similar to this heat packs. So let me first play it once. I'll play it a few times. Okay, and again, I learned this from these physicists, Florent Cascada, Mr. Saucé-san, and Lenka Steboara. So I'll play it a few times because I'll need a little bit some explaining. So do the following experiment. Take a water bottle, and it needs to be very clean, okay? And take this water bottle, fill it with clean water, and put it in your freezer. If you put it in your freezer, then, if everything, the conditions are right, then it's not true that as soon as the water bottle gets below 0, that it will instantly freeze. Okay, what will happen is that it will actually get into what's called a supercooled state. Okay, so a supercooled state is exactly, again, a metastable state. So it's not that, water will be under maybe -4, -5 degrees Celsius, but it will not freeze, because in order to freeze, it will need like a nucleation, it will need a seed to get started. Okay, and so for quite a few hours, maybe 5, 6, 10 hours, the water can actually be in the state in which it's in a metastable state, which has not achieved its most stable form, namely the crystal form, namely ice. Okay, but it will stay in this metastable state. Now, but if you do the following, right? If you take this water bottle, and then there are many ways to do it. Maybe you put some seed in there, maybe you bang it, okay, and this bang will get started. Then as soon as you can see, as you hit it, okay, it will actually start at some end, and it will start crystallize. Okay, so it's exactly when you hit it, it will start crystallize, and exactly this nucleation process, the crystallization process, will continue. Okay, and will go through like a wave through the thing. Now, you probably have looked at the left here. Okay, so now this is basically in crystal form. When you do this, it will not be in exactly crystal form. It will be a little bit slushy. Why? When the water goes from the water state to the crystalline state, since the water state is a higher energy state, it will actually give off energy, right, while crystallizing, right? And because it gives off energy, it actually, while crystallizing, it will actually heat up again, right? And that's why you don't see a solidly frozen. So even if it was maybe -4 degrees before, and after that, some parts will no longer be negative, and so that's why it will have this little slushy form. Okay. So now let's do exactly the same thing again. But now let's, unfortunately, can't see this. So this is really, this is mathematically, these two problems have exactly the same form. Okay, so this nucleation, so what's the form here? The metastable case, what is here, superliquid water, is exactly the PP decoder, the state the PP decoder gets in. And this crystallization, this liquid form, is exactly this. So as soon as you start here, basically the decoder, it sees the boundary, that's the seed. And now that's exactly this crystallization process, okay? So the nucleation that's happening here, which is either putting a seed or an energy, is exactly the boundary. And then this process of going through is exactly the same as what you see in the bottle when the water freezes. Okay, so these two are exactly the same process, the same, if you want, so physical phenomena, or at least the mathematical description is a mathematical phenomena describing this physical thing is exactly the same. Okay. Okay. Yeah, maybe just give, so far I have not said anything. So actually it turns out that these codes go back under a slightly different name. They were called convolutional LDPC codes or time varying or convolution. Go back to a paper by Feldström and Zigangiro. The connection, the way the connection is slightly different. They thought of convolutional codes. Okay, so they're slightly different way of doing. Plus, they were not terminated. Okay, so that corresponds to the unterminated chain that I showed you before. But they introduced, I actually don't really know why, they introduced these kind of codes. Now, because they didn't terminate them, these codes actually didn't show any particular good performance. Okay, so they're very close to the codes I showed you, just slightly different connection pattern, but it didn't have the boundary. Now, the first people actually that had this boundary, so there was quite some work about code words, pseudocode word weights, etc., about these things, and there are quite some people. You see, for example, named Costello quite often, Pascal van Tobel, but many other people in here. Now, one very important development was by is in here. Actually, it happened a little bit earlier. I just mentioned this paper because it won a paper award in I think last year. This was by this list of authors, which in various combinations had written quite a few papers beforehand. And so what is important about the paper is the following. So Costello, and I actually don't know why they did it. At first, they were the first ones in his group that took a chain and had done some termination. Okay, in convolutional codes, there are like terminated convolutional codes, right? And so Costello is working a lot of convolutional codes, so they terminated them, and they run dense evolution. Okay, and they figured out that there was quite some difference in the threshold between these convolutional versions of the basic block codes and the block codes themselves. Okay, so they discovered that if you look at the thresholds, you have quite some different thresholds that you see. And I remember that I think it was already in 2004 that Costello told me that they have actually much better thresholds. But quite frankly, when I heard it at that time, I thought that this simply was a programming mistake. Okay, because if you hear convolutional codes, right, the first thing you hear about convolutional codes is that the state that the initial state, right, that's kind of one of the defining thing, that the initial state goes away, right, within one or two connection widths, right? So whatever, it doesn't matter when you decode convolutional codes, whatever you put at the boundary, that just will influence a little bit what happens at the error rate at the boundary, but it doesn't matter in which state you started. After a few connection widths or memory lengths, the decoding, if whatever the boundary condition is the same. Okay, and so since just at that point, they had called it convolutional codes and so on, and this, so at that point, it really didn't. I didn't really think that this was possible. Okay. Now, somewhat important is it was a student, Cyril Meillasson, and I'll show you a little bit later on. He had actually looked at trying to characterize the map threshold of this is in his thesis, the map threshold of standard codes. Okay, so and I'll show you a little bit the picture then in a second. So you take a standard code, 3.6 code, and let's assume it's for the Gaussian channel, and you want to know how good would this code be if you could do map decoding. Now, at that point, actually, the motivation was kind of weak. I mean, it was clear that you would never be able to do map decoding, but it was still an interesting problem because basically it showed, or if you could characterize it, it would tell you for a particular code that there was basically several thresholds: the code that you can do under iter decoding, the threshold you can do under map decoding, and the Shannon capacity, right? And so if you have all three thresholds, it tells you why you lose, right? You might lose because the decoder is not good, or you might lose because the code is not good, right? And so if you do map decoding and you know the map threshold, and you still know the capacity, you know that the code is not the more perfect code, right? But if you do only BP decoding, then it could simply be that you're not good, right? Because either the code is not good or the decoding is not good, right? So, for example, what David had asked beforehand, if you take the degrees larger and larger, right? Is it the fault of the decoder, or is it the fault of the codes, right? And we'll see in a second, but it turns out that if you take the degrees larger, the codes become exponentially, quickly better and converge their threshold in principle converges to capacity. So if you could do map decoding, it's not the fault of the code. The code actually becomes much better. But unfortunately, if you take this degree, the decoder is not matched well. Okay? So if you can characterize all these thresholds, then it turns out that you kind of know what you have to work on the decoding, or if you have to work on the code. And so why was that important? It was important because when he so he had some upper bound on, I'll tell you in a second, it's called this area threshold Maxwell construction. And these upper bounds, for some cases like the BEC, we were able to show that this is actually equal to the map threshold, but in general, it's just an upper bound. But when we saw the thresholds of these convolutional codes, right, then we immediately saw that these were actually the thresholds of these map decoding things, right? And so then it became immediately clear that this was not, just a good construction, but that something, quite fundamental must be going on if you just do this in a chain and suddenly you get the map threshold. So, without, I guess, what Cyril had done here, it would have been, not clear that, we would have really looked at that so closely, because it wouldn't have been clear that there's something so fundamental going on. Okay, good. Now, okay, I'll tell you a little bit in a second. There is right now basically 3 different kinds of proofs that are out there, and I'll tell you just a little bit what the different approaches, not really what the proofs are. And particular one, the one that's probably right now the easiest one is some and again, there's several papers out. There's some paper by, group of Henry and Narayan, and then there's 2 or 3 students, but there's several of them papers out. And this is based on what's called potential function. I'll tell you in a second a little bit what these things are. These are probably by now the kind of maybe simplest ways to prove things. There were also, in this line of work, some previous work by Tanaka and Takeyoshi, Japanese physicists that come quite often to the Information Theory Society, that had also used ideas of potential function, but had not quite, the proof was not quite complete. And there was also a paper by Andrea Montanari for compressive sensing, in which you can also use these ideas, which had also used potential functions. So there's also some other work. Okay, so I hope I have now given a little bit some credit, but there's much else going on. If you look at, so in arXiv, there are maybe right now 60, 70 papers on various either proofs or applications of spatial structure, spatial coupling, not just the coding, compressive sensing, constraint satisfaction problems, some other, graphical models, whatever, independence set, coloring, etc. And so I think the best reference right now is arXiv to go there. And these are some of the words where people have used this and or what people have been working on. Okay, now let me give you now maybe a little bit some maybe summary and maybe then just point out a few maybe interesting questions or practical problems or practical issues. Okay, so first of all, what do we know at the end about spatial coupling? I only talked about the BC, okay? But what do we know? Well, it turns out that for these codes do not just achieve capacity for the BEC, but they actually achieve capacity for larger class of channel. For example, any binary input-output symmetric memoryless channel, these codes achieve capacity. And actually, I'll tell you in a second, the nice thing is that they do universally. So meaning one and the same code is good for any such channel. The only thing you need to know is its capacity. You don't need to know when you construct the code whether or not it's a Gaussian channel or a BC or a BSC. You do need to know still up to now at the decoder. Okay, so we don't have right now efficient rules to do the decoding in a universal manner. You can do it, but it's not very efficient. But at least when you construct the code, it doesn't really matter. Okay, the only matter that the code really depends on is that it has enough mutual information. Okay, so that's kind of nice. And then I tell you maybe a little bit about the block length behavior. Encoding, decoding, I'll tell you a little bit what these things mean later on. Encoding is fairly easy to do. Decoding is fine. The only thing is, for example, if you ever heard of polar codes, polar codes have a decoding complexity, which is quite good. Okay, so if you look at the gap to capacity, let this be delta. So let's assume you have a capacity channel of a half, and you want to transmit at 0.499. Okay, so then the gap would be 0.001. Okay, so that's the gap to capacity. Now, if you now let this gap to capacity go to 0, and you're looking at how the complexity has to grow as a function of the gap, then polar codes are quite nice. Per bit, the complexity only grows like log 1 over delta. Okay, so that's a very mild behavior. That's very good. Okay. Now, for spatially coupled one here, this is only, it's not a proof, but we think that it behaves like 1 over delta. Okay, I can give you the argument why, but that's quite a little bit worse. What is the reason? I don't think it has too much to do with the code itself. The reason is that spatially coupled, or in general, iterative codes inherently have a parallel decoding structure, versus polar codes inherently have a successive decoding structure. Okay, so I think that there's probably a way to take polar codes and decode them in a more parallel fashion, but then use more complexity. And there's probably spatially coupled code and decode them in a more serial fashion and have less complexity. So I think one of the nice open questions is to check whether or not both kind of codes, right? And the advantage to both. So for example, for something you might only be interested in the power and then complexity important, but for some other ones, you might need high throughput. And then if you need high throughput, then maybe polar codes might not, in the standard version, might not be the way to go, right? And so it would be nice to find both for polar codes and for spatially coupled codes ways to decode them such that there's a trade-off between basically the type of parallelism you have and the kind of energy that you need to spend per bit. Okay. So now let me get a little bit, just tell you a little bit. So let's assume we have again capacity half, since this is what we always talk about. So if you take the 3.6 code, so these are the thresholds, right? So it should be a half, but for BC from 43%, it jumps up to about 45%. 8.8, right? Now, if you do the Gaussian channel, right, then it jumps up to, it's about 0.48, so slightly worse. And if you do the BSC is actually the kind of the worst channel to code over. So you get about 0.47%, right? And it should be about 50. But now remember, if we go up now in the degree, if we did this for the uncoupled system, this would be all go down, okay? But fortunately, if you do this for the coupled system, then actually all the thresholds go up, okay? You can see the threshold in each of these phases goes up. And this goes up actually rather quickly, okay? So this goes up exponentially fast. And the nice thing is that's so universally, okay? So for example, if you, you can have a universal lower bound that says that the rate you can achieve, that's the rate you should be able to achieve, okay? And then this thing here, it's a little bit hard to read. The only thing that's important is that it's e to the minus, and that's the right degree, okay? And then these are just constants here, basically. So it goes exponentially fast. So this is the gap to capacity. And this is universally over any channel. This gap to capacity will go down exponentially fast. Right? So that's kind of nice to, if you want codes that universally achieve capacity, they automatically do so. There's nothing special you need to do, no particular degree distribution, nothing. Okay? Just pick regular codes, pick the degree large enough, and you know whether the channel is you can get close to capacity.
With capacity, is it easy and easy to two extremes?
So there are two extremes in many ways. I don't have a, because this is a universal bound, just done universally. Yeah. So if you want to actually compute specific thresholds, there's still some. So there's an expression in there, and then you have to evaluate this expression by plugging in a fixed, so a distribution. Okay. So there's some numerics involved if you want a specific threshold. You can control it because it's just a fixed point of some iteration, and I guess you can control. I mean, these are just similar to the fixed point that I've written down before. Okay, but I don't have an explicit, for the BSC, for example, I don't have an explicit expression of the exact threshold for the BSC as a function of the degree. Okay.
Maybe we would compare with gradient and particular capacity with BSC and
yeah, maybe it's not easy to get a handle on the exact threshold. Okay, so there might, but we don't know right now how to do it. But it's known in many other ways that BSC and BEC are extremal, right? So in terms of, let's say, the exponents and so on. So in many ways that's known, okay? But not in terms of the threshold. It looks like that way, but I don't know for sure. Okay, now, okay, let's get to one of the issues. That's the yes.
So just to connect those numbers, your earlier paper,
What?
the numbers that you have, so can you correct that?
Right.
The numbers were already predicted in that paper with the math threshold detector.
Yes.
So all the numbers were math threshold.
Yes. So where did I have this? Oh, no, it's later. Where did I have this? Yeah. Right.
Yeah, the maximum construction.
Yes. Yes. So these numbers, the reason we basically found out because particular numbers like this we had worked on is where I mean you can go with this is 488,416. Okay, so after a while you're working and you know it up to the 7th digit, and then if you see a number that has exactly the same number of digits, that precision you somehow suspect that something is working. Right. Good. Okay, now let's get to rate loss. So remember, right? So we have a little bit some problem here, and because if it wasn't for the rate loss, right, this would be absolutely amazing, right? Because I could pick whatever chain length I wanted. I would get extremely close to capacity. One thing that I didn't mention is that it's very easy to construct spatially coupled codes that have no error floor, right? Why is that? Because I don't need any degree 2 nodes. So I can have large enough nodes, and then for example, if the node degree is at least 5, you have provably with high probability an expander, and if it's an expander, you have provably that it has an error correcting radius, and so you have even exponential decay, right? So, this is all really, really nice. The only caveat is that you need some, you have this rate loss, right? You have some extra checks at the boundary. This is exactly the seed that you need in the nucleation process. That's in order to get things started, right? And so the question is, how much rate loss do you have? Well, so this is the standard chain, right, which has these things at both sides. Well, if it's like this, right, then we can just compute. So maybe let's just move it over to a side that's just, that's just moving things. then what you can see, right, if you look at these two pictures, so this is, let's say, a 3.6, right? So then you see there are two extra ones, but if you took, let's say, a 4.8, right, you can see there would even be three extra ones here, right? And so if you go up higher and higher, you would see an extra W minus 1 or degree minus 1 extra check nodes. And so what this would mean is that so you have so many variable nodes, you have so many check nodes if you figure it out. So it means that the rate that you get is the rate that you should get, but then there's a penalty, okay? And this penalty is, roughly the degree minus 1 over the length of the chain, okay? These more or less is just the constant here, right? And so that's of course a little bit a problem, because if you pick the degree very large, and then this means you would have to make the chain fairly large, right? So the question is if that's the best thing you can do. And you can do a little bit better, okay? So for example, one thing you can do is you don't need that the chain starts on both sides, right? It's enough that this process starts on one side and then simply goes. So for example, one thing you can do is you can simply, in this case here, put all these things together, and then this process will not start on this side, will only start on this side, but at least you have halved, for example, the rate, the rate loss. Okay, so these things you can, for example, get rid of, right? So, okay, fine. So, factor half, okay, that's something. Now it turns out actually you can do even better. Okay, so what would be in my mind, what's the naive physics analogy, right? In order to get this process started, think of it as a ball, right? In order to get the process started, you need to give it some push. Now, the higher the degree is, kind of the larger the push has to be. So if that's degree 3, okay, so you need to give it some push. That means a certain rate loss that you have. But what would happen, for example, if you have a larger degree, right? So in your mind, and that was also in our mind initially as well, you have to give it more push, right? So it means you have automatically higher rate loss, right? Now it turns out that's actually not quite true. It's actually a little bit nicer than this. So, and what do I mean with this? Well, the person that observed it was actually Kenta, and that's the following. So you have still the situation like this, and now the rate loss is basically these three checks you have here, okay? Now Kenta simply tried, and what did he do? He simply put all these, he simply deleted the last DL minus 2. So he has only a single one extra that it's checked. So now your loss is only 1. It should really be 3, but your loss is only 1, okay? Now if you look locally kind of at the rate of this code, however you define it, that's kind of strange, because the rate of the code there locally is actually above capacity, and you might be slightly worried that that can't end very well, okay? But it actually works, okay? And so if you do that, so now it's a little bit better, because now your rate loss is just a constant. It doesn't depend, just depends on the rate, but it's no longer depends on the degree. It's just 1 over L now. It's a constant, right? Which is already better. It doesn't depend on the degree. And so now, what is kind of the physics intuition here? Why can this work? Well, it can work, okay, because even though you might have to push it harder in the beginning, okay, really think of that this ball has momentum, right? And what we need is not that at the end, when the thing is done, that this rolls over with constant speed and it goes over. But all we need is that this wave just finishes until the very end, okay? And so this means that actually at the very end, we can get some information, whatever information we initially had to put into the code to get it started, some amount of this information we can actually get out at the end, okay? So how should you think about it? Think of this spatially coupled structure, and think of the BEC, right? And now simply cut somewhere the edges that you have somewhere, right? So there are two types of information that you can have. So one type of information is basically information, let's assume that's the future, okay, this is the wave. So one type of information is that the decoder at this point has decoded something, and now along an edge, this information is carried over to the right, right? So this is information that basically helps the next slice to decode. The other type of information is that something in the future is decoded somewhere and things go backwards, okay? And so you have both flows of information, and you can actually compute these two flows of information, and you will see that the flow of information going from the left to the right, so to the future, is much larger than the flow of left to the right, from right to the left, okay? Now, but the flow from the right to the left at the end you don't need, okay? There's nothing, at the end when you're done, there's nothing else, there's nobody else you have to help, okay? You're done. So this means that actually, in principle, you should be able to get a lot of the information that you put in initially back. And we have some kind of bounds, but unfortunately nothing reversed. So one of, I think, a very nice open problem is it's not at this point, okay, it's not even clear whether or not, just, in principle, you actually have a rate loss or not. Okay, so if you have if you knew exactly the optimum way of how to get things started and the optimum way of how to end things, it's not 100% sure, okay, that you actually have to pay for this. Okay, it might very well be that you can get all the information out. Okay, this might not be the way to construct it because maybe it's not a very stable way of doing it. But for example, a very nice open problem to think about it is to think about information periodic bounds that might either prove that there's an absolute lower bound that you need to, for the spatial coupling to do, or maybe there is no such thing, and then maybe if you see there is no such thing, come up with constructions that basically bring this rate loss down to something much smaller. Okay, that would, practically speaking, make a huge difference. Okay, but currently it's not exactly clear, so we have various constructions, but still, so far, the best rate loss we know is of order 1 over L, and there's nothing better than that. Okay, next thing, again, it's kind of hard to see. Yes?
Before you go to that, you've never proved it without it.
Yeah, which
You've never
one?
proved that you can get to the math.
I'll show you at the end. I'll show you a little bit something. Okay, I'll show you the 3 ways of how to do the proof. I'm not sure if.
But I still, sorry, I thought I understood your whole story, but
Right.
then I thought more about it. That's
Right.
very interesting. Can I ask you a question now?
Sure.
So your example was that you say that, okay, the degree is getting higher and higher globally, but the first one, because you have some visualization, you can get by with epsilon greater than 1/3, right? That would be the time.
Right.
But that doesn't show that you can actually do better.
This has nothing to do with the proof. This is just to show you a simple way, a simple argument that there's something fundamentally different going on between. Okay. The proof will have nothing to do with it. Okay. The proof is not one line. Okay. This was a slightly simpler argument to do this. I'll show you then, just the 3 ways of how you can attack the proof. I will not show you, the real proof because it's a little bit longer. Okay. There's no one line argument. Okay. Good. So now, how do codes, how do these codes behave? Well, you can look at what's called finite length scaling. So you can look at, everything we talked about here in our thresholds. Right? Everything is the infinite limit. What is the threshold, the maximum thing? But in practice, you're not looking at the infinite limit. You're looking at a code of like maybe 10,000, and you want to know how things behave, right? And so the question is, how do things behave? And you can look at finite length scaling results, and they tell you that the error probability has the following components. So remember what this thing is. L is the length here, M is the size of each component, and W is here the connection width. And so what happens is here that on the one hand, you have a term like e to the minus m times delta squared. Okay, so what is delta squared here? Delta squared is the gap to capacity. Okay, so that's how close you want to get to capacity. If you want maybe 1% close or 2% close. Okay, now if you ever looked at scaling results like this, if it wasn't for this part here, and if this was the block length, then this is actually very good. This is exactly how optimum codes behave. Okay, e to the minus n delta squared. That's exactly, if you ever looked at error exponents, okay, you will see that the error probability behaves like e to the minus some constant, okay, and this constant depends on where you're operating, times n, right? So the n is here, you think of this the block length, and what's the constant? The constant scales, if you look at how the constant behaves as a function of how close your capacity, the constant is first, the dominating term is exactly the delta squared, okay? So this behaves up to, the constants here. This has exactly the behavior like you would see in optimum codes, okay? Unfortunately, m is not the actual block length here, right? M is the block length of each component, but there's also an L that you have in here, right? And so the point is now that the whole block length is L times M. And so unfortunately, you don't have here L times M on top. You just have M in here, right? So these parts are not so important. These parts are, rather minor. But so the question is now basically you have 2 kinds of losses. One loss is because the curves are not infinitely steep, right? The curve only have a finite steepness. That's the finite length skipping. But the other loss is because you lose something at the boundary, and at the boundary you lose something which we saw is proportional to 1 over the length, right? So you have 2 kinds of losses. One is because you're not at infinite length, okay? So you have some gap. And the other one is because you have a rate loss gap. And so the question is how you basically should choose L versus M. And it turns out the right scaling should be that L should be roughly the block length to 1/3, and the M should be the block length to 2/3. Okay, I don't have it written somewhere. And if you put this together, then you will see that, I didn't write it down somewhere. Yeah, you will see that the gap to capacity. Okay, you have here n to the minus 1/3, whereas for optimum codes you have n to the minus 1/2, and for polar codes you have here roughly n to the minus 1/4. Okay, so these codes are somewhere between. This is the optimum behavior. Polar codes need roughly the square of the block length, and these codes are somewhere pretty much exactly in between. Okay, so that's partially good news, partially bad news. They're not as good as optimum codes, but they're not exactly terrible either. Okay, fine. You can do also window decoding, but maybe let me skip this. So, what in general, to the decoding of the whole thing, you simply look at the window size and just do the decoding in the window, and then just simply move the window. If you pick the window roughly 2-3 times like the constraint width, then you can get to arbitrarily close again, exponentially fast converges to the standard threshold, so you don't lose much, and that can make a big difference in practical systems. Okay, and so again, there was already Felstorm and Zagangreff done, the Landmeyer, and so on. So there were quite a few works on various windows. Okay, so let me just, before I talk a little bit about how to characterize these thresholds and potentially how to prove things, so let me just, what is the main message that we have? So the main message is that if you take a standard code, okay, like LDBC, turbo codes, whatever, then this will have a BP threshold and it will have a map threshold. If you take this code and you spatially coupled and you again run BP, then its BP threshold will now be the map threshold of the underlying code. Okay, so that's slightly sloppy speaking the main behavior that it has, and because we basically get now on the BP the highest possible threshold we can have, namely the map threshold. We talk about threshold saturation. And the nice thing is also that they're universally capacity achieving, and we have seen that one of the downsides is that we have this termination, and because due to the termination we have some rate loss, and because of the rate loss we can't pick the L too small, so this is not a construction of codes that are very short. Okay, so maybe if you have 10 or 20,000, then it would make sense to look at these codes, but if you have a code of only length whatever 1,000, then it probably doesn't make sense. Okay, good. How much time do we still have just to time limit? 45 minutes? Okay. So there are currently 3 different ways of, so right now what I'm going to do is I'm going to tell you 3 different characterizations, and right now they will all be for the BC, because again, for the BC the characterization is much easier and has nice graphical interpretation. And so there are 3 different ways of characterizing the threshold that I talked about, which I said is the map threshold, but this will only come out as a result of it. And these 3 different representations, each of them has also a kind of a different style of proof attached to it. Okay, so I'll tell you what the characterization is, and then I'll tell you a little bit, how you might turn this into a proof. Okay. So
area is the best threshold in the
So this area threshold, I'll tell you now why it's called the area threshold, will turn out to be equal to the map threshold, and this is the threshold of these spatially coupled, and is the threshold of the underlying code. Okay, but this comes out as a result of the thing. Okay, so the initial characterization is that it's area threshold, and then it turns out that through other arguments, it turns out that it's the map threshold, and it's also the map threshold of the underlying. Okay, so let me tell you now a little bit what these 3 characterizations. So the first one is this Maxwell characterization. So this characterization actually came before spatially coupled, and this has to do with this work by Cyril Meillasson. And this came out of our desire to characterize the map threshold of the underlying code. So let me just tell you what the characterization is. So remember we had this curve, this exit curve here, right? And so this was the BP threshold, and so this exit curve characterizes the BP threshold, okay? Now, what turns out is that this exit curve also characterizes another threshold, and that's what's called the area threshold. And graphically, and that's why it's called the area threshold, this goes as follows. You take this exit curve that you have, And now you integrate from the right until the area that's under this curve, okay, is equal to the rate of the code. Right? So you do this, and this will give you a particular threshold here. Right? So if you do this right here, you will see that 0.4881, whatever it is. Okay? And so this is for the physics code. So that's one area threshold. And so now, why is this called, why is this construction to getting this threshold here the Maxwell construction, and what's the significance of this point? Okay, so why is it called, sorry. Don't look. Don't look. How can I get that?
You're at 10%.
Huh?
You better speak fast. You're at 10% battery left.
Oh, okay. Yeah, no.
I can speak longer.
No, I can relax, okay. Too bad for you. Okay, so how does this go? So let's go over this again. So remember, I told you in the beginning that if you take this whole curve, all a set of fixed points, you get a particular curve here, right? Typically, we only look at the top part and then when it drops. But if you look at the whole part here, you get a curve. And this curve has a very easy characterization. If you remember, the epsilon as a function of x was just this expression, right? So very easy characterization. So this whole curve is just in parametric form. The curve, epsilon as a function of x, comma x, right? That's this curve. Now, if you integrate the thing that's inside here, the thing that's inside this region here, or you integrate 1 minus the region that's in here, okay, you can just do this. So you just write this down, the exit, so that the exit curve times epsilon thing, you just compute this. You will find that miraculously, this is also the rate of the code. Okay, so the curve inside here is also the rate of the code. Okay, just turns out. Good, so what we have now? So now we have the following, right? So we know that by the Maxwell construction, right, we know that the curve here, or the area here, from here up to here, that's the rate of the code. And we know that this funny C-shaped curve, right, is also the rate of the code, right? So now look at these two things and put them together. You will see that they are not exactly the same, right? They're overlapping. So there's some part that's in both of them, right? This part here that's in both of them. And there's some part that's only in one, and there's some part that's only in the other one, right? But since the two areas are the same, it must be true that this area is equal to this area, right? That's just because you have two equal areas, you overlap them. Whatever is not common, only belongs to A or only belongs to B, must be the same, okay? So another way to characterize the threshold would actually have been, take a vertical line here such that these two areas are equal, okay? And so now what does that have to do with the Maxwell construction? Why is that, why is that relevant? Well, if you think back when you, learned like the ideal gas equation or the equation of state, right? Then this went as follows. Well, so you have, think if you have pressure, right? You have volume, and you have a certain number of particles, right? And then that's just the Boltzmann constant, and that's the temperature, right? So the ideal equation of state the equation of state for an ideal gas is this particular equation here, how the relationship between, the pressure, the temperature, and the volume, and the number of particles that you have. Now, this one is a reasonable approximation in some regime, but in some other regimes, if you actually make measurements, it's not very good. So Van der Waal came up with a slightly different equation, and this equation is like this. When you compare it to this, it's exactly the same right-hand side, but the left-hand side is a little bit different, right? And what were his considerations? This is also not, the real physical system, but it's slightly closer. What were his considerations? Well, his consideration was the following. Well, you don't really have volume V, right? Because particles are not ideal point masses. Particles have some volume too, okay? And so if you have n particles with a certain radius, okay, and I take some ideal assumption, then those particles themselves take some volume away. So the effective volume is slightly less. Namely, it's the volume you have minus whatever the volume per particle is times n. Okay? So that's why he replaced the V with this V minus Vn, right? And then for the pressure, okay, he had also an argument, and that has to do that particles themselves also have attracting forces. Okay, so particles themselves have some kind of attraction, and so if you take this attraction into account, and in particular take into account that if you have a container, that most of the particles, if you go towards the boundary, that most particles would be on one side of the end. So let's assume I have my box here, and I'm looking at the pressure that I have that the wall exerts. Well, this pressure is in effect slightly different. Why? Because most of the particles are on one side, and so if I'm in the middle, then there's basically equal number of particles in each direction, and then there's no attracting force. But if I'm on the boundary, and I have most of the particles in the middle, then there's some attracting force inwards, and that basically increases the pressure. Okay, so it's a model. Doesn't mean that's 100% physically correct, but it was an intuition. And so he added that term here. And so if you look at the van der Waals equation of state, then this has the following behavior. So this is the volume, right? And this thing here is the pressure. And so this is a constant temperature, right? So what should happen is, right, that as you decrease the volume, the pressure should go up, right? But if you plot for particular parameters t and so on, if you plot it, you will see that there's this little small kink that you have here, right? And so this equation, which came from theoretical consideration, is just not as accurate as is physically not quite meaningful in this regime. And so it was Maxwell who came in and kind of fixed this equation. Okay, so again, even after it's fixed, this is not 100% physical correct picture, but it made it physically more plausible, and it's a much better approximation. And his argument was the following: if you look at kind of some volume here, right, then this is actually work that's performed. Okay, so if you just have to, if you push something against the pressure, then you have to do some work. And so basically these two areas, so he said the following, unfortunately it's very hard to see. He said take this curve that you get from van der Waals, okay, and in order to make it physically meaningful, simply substitute with the following. You take this, and now you put a vertical line here, and where do you put the vertical line? You put it exactly in such a way that these two areas agree. And so the idea is that there's basically, work gained and work, basically being performed, and if these two things are exactly in balance, then that's the right physical interpretation. Now, what is, so this is what's called in physics the Maxwell construction, and for the BC, you have exactly the same thing. So it turns out that there's a decoder, you can write a decoder which is called the Maxwell decoder, in which this area here that you have here is kind of guesses that a decoder has to provide to you, and this area here, so this is now information of work, and this area here is kind of confirmations about the guesses you get later on, and exactly when these two things are balanced, right, then that's exactly the, where the map threshold should be situated. Okay, so this is, the reason that we had originally looked at trying to characterize for the BC the map threshold, and it turns out that indeed at that point we could prove together with Andrea Montanari that indeed exactly this area here, together with this interpretation of the Maxwell decoder, that exactly this point here will be for certain classes of LVDC codes will be the map threshold, and for general channels that was at that point simply an upper bound. Okay, so this was the Maxwell construction, and just I show you now what these curves look like for these exit curves look like for the coupled case. So if you take the coupled case and you plot these, so let me just run it again because it was fast. So what is this experiment that I show you here? You take a coupled chain, right? And what you do is you simply increase the block length. And now for each block length, I plot this exit curve. Okay, it's simply the curve that you have. So let's do it again. Now for very small block lengths, this exit curve is actually much to the right here. And that's simply because there's quite some, if you have very short block length, you have quite some rate loss. And so the map threshold actually for that is not equal to this map threshold here, because you basically have a code of very different rate. Okay? But the question is what happens when the chain length becomes large? Then the rate loss becomes asymptotically negligible. And then it turns out that you see that the curve that you see here, which unfortunately you can't see very well, the one that's lightly shaded gray, that's the exit curve of the underlying code. And you will see that for the specially coupled code, this exit curve seems to be stuck exactly, and that's exactly this area threshold. Okay, so that exactly goes here to the area threshold. So so what is this connection between what is this connection between the map threshold and this area threshold? So why is that area threshold an upper bound? Okay, what does this have to do? The basic idea is the following. What is up this curve? What is this curve here, right? This curve is the best estimate that a greedy algorithm has about the bits that you can decode. Okay, so that's the best bit error probability that it can have that the greedy algorithm will provide for you. Okay, now let's assume that instead of having this curve plotted for a greedy algorithm, let's assume that you had this curve if you actually looked at a map decoder. Okay, so let's assume you looked at a map decoder, and again you looked at the error probability you would get for the map decoder for the best code that you would have. Now, where would this curve be with respect to the map decoder, right? Well, the greedy algorithm is a feasible decoder, but it's not the optimum decoder, right? So this means the map decoder must be doing better, right? The map decoder must somewhere be, must have a curve that's somewhere upper bounded by this BP. Okay, you all agree? I mean, map decoder cannot be worse than BP decoder, so if you looked at the best estimator for the map, it must be below the best estimate of the BP. Okay, now if you actually had now this map curve, right? Then it turns out that this is exactly the height of this curve is exactly the derivative of the conditional entropy with respect to the channel parameter. Okay, so this is what I wrote down here. I don't think I want to necessarily go through it, but this, if you look at the conditional entropies, you have the vector x and you have your observation y. Okay, then so what do you look at? So forget about the r for a second. So just look at the vector. So you have a code, as we said, you have a code with x and you have your observation y, right? So now look at this quantity here. Now here you have the rate of the code. What is the rate of the code? The rate of the code can also be written down like this, but it's the entropy of x if the erasure probability is 1. Right? If the erasure probability is 1, then you get no information, and then since you have a uniform probability distribution on the code words, then the entropy on the code words, if you divide by n, that's exactly the rate. Okay, so rate minus this conditional entropy at parameter epsilon is simply the difference of the conditional entropies, but at certain different parameters. This parameter 1, and this is the parameter we're looking at. Okay, so now if you have a difference of here, then it's quite naturally that you write this as an integral of the derivative. Right? So, so you have a function, right? You validate 2 points, maybe epsilon being 1 and epsilon being whatever epsilon area. You write this now as an integral of the derivative of this quantity with respect to epsilon, and evaluate the 2 endpoints, right? So that's just the fundamental theorem of calculus. And so now you simply start evaluating this, right? So instead of now the total derivative, you write this down as partial derivatives. So what do I mean now with partial derivatives? Well, in general, you have one channel parameter, right? Every bit goes through the same channel parameter. But what you could think of is the following. You have n bits, and simply think that every bit goes for its own channel with its own parameter. They just happen to be all the same, right? So then what is this derivative here? Instead of writing this as total derivative with respect to epsilon, write this as the sum of the derivatives with respect to epsilon parameter I. Okay, so that's the ith channel that you think of. Now, instead of turning one big knob in which the channel gets changed, you first change a little bit the first channel, then a little bit the second channel, then a little bit the third, until you have changed them all. Okay, and you look at the effect of all. Okay, so this is the line here. And now for the erasure channel, so now you simply write down, you use the chain rule here, so you have h of x given y, you write it as h of xi given y minus the h of the rest given this. Okay. Now you realize that this part here doesn't depend actually on the ith channel parameter anymore, so you can drop that. So you have only this left. And at the end, if you think about this parameter here, it turns out that you can actually explicitly write this down. Okay, so this parameter here you can write down explicitly as the h of xi given all the observations except the observation itself. So what is this? This is the entropy of the ith bit given all the observations except the observation of the bit itself. Okay, so, and now remember, this should look very familiar, because what is this? This is exactly what we did in iterative decoding. In iterative decoding, we looked at the estimate of the iterative decoder of the bit xi, knowing all the observations except the observation itself. Okay, so that's exactly what we call the exit function. But now we simply use the fact that the exit function must be, this estimate must be worse than the estimate here, right? But the integral of the exit function, that's exactly what we have here, right? And so if we exactly here such that this is again the rate of the code, then we cancel the rate, okay? And we see that if we are at this point here, then what we see is that we conclude that the conditional entropy must actually be, if we were slightly more to the right, it would turn out that the conditional entropy would actually have to be strictly positive. And if the conditional entropy is strictly positive, then even the map decoder cannot. Okay, so that's where this whole thing comes in. For the BC, it's slightly easier. For the general case, it's the proof is a little bit more complicated. But that's basically why originally this quantity appeared. And now you can hopefully, appreciate why we use this exit function, this funny thing here, right, which had to do exactly with this expression here, right, rather than some other expression.
How do you go from that?
From which one?
From this fourth line back.
You tell me when to stop. Here?
Go on. No, one more. Yes, how do you go from that?
So the point is, if the yi, if the yi itself is, so this is epsilon, so if you condition now that epsilon is either, that this bit is either known or not, so it's either, if it's known, the bit, then there's no entropy is 0. And if it's not known, and you change a little bit the epsilon, then it's exactly the epsilon times this expression. You take the derivative of epsilon, you just get the expression.
Linear this one.
Okay.
The condition
Right. It's linear and epsilon. Okay.
But this is very specific to the ratio channel.
The general case was slightly different, but again, this is easy to show. General case is not so easy to show.
So this is true for general case as well.
So this is an upper bound, and for the same reasoning, the conclusion is exactly true. Okay, but it doesn't go just like that. Okay. Good. So yeah. So now it's exactly this characterization that was originally used to prove this. So this right now, what I just told you is how the, why is that, why does this have anything to do with map? So this is just the uncoupled system. Why is map related to this particular threshold here? Okay. Now this doesn't quite explain how the proof goes for the spatially coupled one. So for the proof for the spatially coupled one, really has to do with this picture here. Okay. Essentially, what we do is we construct explicitly. So the idea is that, the idea is exactly this picture, okay? So what we construct is explicitly a family of fixed points that exactly when you project them down to this exit function here, trace out something like this. Namely, on top, it looks like the BP exit curve, and then it drops somewhere, okay? So we trace out, we explicitly construct proof that there is such a family. And whenever you have a family of such fixed points that smoothly, for every such parameter, then in the same way as I showed you before and here, that that this curve here, that this integral here is equal to the rate, that's true in general. So as soon as you have a family, each of these points is a fixed point. As soon as I give you a family of fixed points that smoothly trace out a curve, that the area inside this family must be equal to the rate of the code. Okay, so that's just a general thing that you show. And so we basically explicitly construct points that trace out, that look something like this, as the exit curve here, okay? We don't know where this point is. We just know that it's steep and then has like this. And so once we know that the rate has to be equal to the rate of the curve, and that this means it has to be exactly at this point, okay? That's a little bit vague, but it basically uses exactly this intuition of the picture that I showed you. Okay, now there's another thing. Yes.
We go back to
right.
That nice animation.
Yes.
It's very nice, but what is actually what is the?
So
yeah, what is this thing that is increasing?
So this is the length, the block length is increasing.
You mean the chain length?
The chain length. Okay. So what it shows is that originally that this exit curve looks different, and this more to the right is not surprising because the rate is much smaller. Right? If you have a very small block length, if you have a very small L, and you have a rate loss in the boundary, then the rate of the code can be much smaller than the original, right? So that the threshold can move to the right is not surprising. If you take, let's say, if you take the initial picture, right? These pictures look like this. This is maybe for a chain length of length 3.
So right means bad.
Right means good. It means
right
that it means that it can. this is the entropy. So it means it can tolerate that much, that much of channel.
So if you increase L, it gets worse and worse.
Yes.
Why?
Because it's basically nested, right? So if you take something that has L5 and you take L6, then the L5 is actually containing the L6, but it's basically at the boundary. I give you some extra information.
L5 contains
Because if I knew from one boundary, if I tell you some bits at the boundary, then you basically have a smaller code, right? Okay, so it's clear that this cannot get better. Okay, so the way you prove it is you actually prove something about the limiting length, right? And that includes any length you want, right? But
it's the same number, right?
yes, but if you have the boundary, just think of the structure, and now I tell you a few extra bits. I tell you basically a whole segment. I tell you the bits. Then what you have left is exactly a code of length 1 less, right? Clear? So they're nested. So it's clear that they get worse the longer the length.
But the larger L, the less the rate loss, right?
Right. So the point is what you need to show is that even what's important here is that even if L goes to infinity, this doesn't go back to the original 3.6 to the uncoupled one, but it gets stuck at this area. Okay? It's just another way of showing this threshold saturation. Even for L to infinity, this exit curve eventually will become exactly this. Will become exactly this square. Okay, go up and go along here.
That's good. There's a proof then.
Yes. So the proof goes exactly by proving. So how does the proof go? The proof goes by showing that for this recursion that I had before, that I can construct fixed points that exactly trace out. If you plot them on the thing, they trace out exactly something like this. Goes down quick, and then on top it exactly traces out this curve. Okay. And whenever you have a set of fixed points that do that, you know that the rate of the area inside must be the rate of the code. That's just the general, that's just an identity, okay, that you have. And so where then must this point be? It must be the area threshold, because that's exactly the definition of that. Okay, so that's how basically the proof. Okay? Any other questions? Good. So now let me show you two other characterizations, which might be nice for people that know exit. So if you ever have seen exit charts, not exit curves, but exit charts, perhaps this might be quite useful. So remember, so let's go back to the BEC. Okay, so for the BEC, you have these exit curves, which rather than looking at the whole recursion, let's separate out what happens in the variable node and in the check node. Okay, so remember we had always this x as a function of y, and then the y is a function of x. So let me just give this two names. So let me call this thing here lambda of x, and let me call this here rho of x. Okay. Then simply this x will be epsilon lambda of y, and this y will be 1 minus rho of 1 minus x. Right. So these are simply again the equation that I've shown you before. Nothing new here. Just I give it names. And so now this was introduced by Stefan ten Brink. If you want to look at the BEC, an equivalent way for the uncoupled system to characterize it is the following. You plot these two curves, namely x is a function of y, and y is a function of x. And so what do you do here? So here you plot you plot x as a function of y. Okay, that's this curve here. And here this is x, so you basically turn this curve around. So this is the y as a function of x. This is this curve here. Okay, so you think of this. And so now iterative decoding is a very simple description. You start at epsilon, and now you simply bounce between these two iterations back and forth. Okay, so that's the exit chart characterization. And so now, how do you see the fixed point in here? Well, this is as a function of epsilon. If you move epsilon up, then this bottom curve will simply move up. So for example, if I go, so this is simply now the description. So this is for 0.35, that's fine. Everything it goes to 0. You see that it will go to 0. So that's equivalent to the intervolution. Sorry. But if you, but what would happen? Okay, if you moved up this this curve here, if you moved up this curve here, you can see that the top here, that is exactly epsilon. So if you move this down small enough, then these two will not overlap, and you bounce back and forth. Okay, and you see the threshold when you move it up just high enough that these curves will touch. So what is the characterization of the area threshold in terms of this? It's slightly different. What you now do is you can actually overlap, okay? But if you now overlap and you did iterative decoding, you would get stuck up here, right? So it wouldn't be done. But if you look at the area threshold, what happens is that the dp threshold is the matching of the two curves, And the area threshold is the two curves can overlap, but they cannot overlap too much. Okay, the worst they can overlap is that these two areas imbalance. So this area has to be always bigger than equal than this area. Okay, they cannot overlap. So if you have a one-dimensional system, so that's true for any one-dimensional system, it's nothing to do with coding. If you have something, if you ever used exit charts, you have a system how to do with exit charts. If you now just want to spatially couple it, it's a one-dimensional system. Instead of determining the threshold like this, determine the threshold like this, and that's the threshold of the spatially coupled system. Okay, so you can clearly see that it's larger because you can move it up higher. Okay, so that's kind of a nice characterization if you're really familiar with exit charts. Okay, the proof using that goes slightly different. The proof goes by going to a continuous system, and so you go to a continuous system rather than a grid system, and then using analysis to show that that exactly this wave that we have seen. So now the wave is no longer a discrete wave, but it's a continuous wave, and you simply show that this set of differential equations that you now get has a wave equation, has a running wave as a solution, and this wave will either go to the left, let's say, which means decoding, will go to the right, which means it doesn't decode, and exactly where it's stuck, that's the threshold. Okay, so that's how the proof goes using this system. And finally, the potential function characterization. So, as I said, this was originally by Takeuchi and Tanaka, but slightly different formulation. And the one here that I show you is by Henry Pfister. So this goes as follows. That's a very nice characterization. So this goes as follows. You define an integral, okay, which will turn out to be the potential function. So what is this potential function? Well, this is for the BC here, so it's the simplest case. Look at this thing here, right? This thing hopefully looks familiar. This is exactly the dense evolution equation, except that now you have lambda and rho, except for specific polynomials. So simply think of lambda as the power to the dl minus 1, and think of rho as the power to the dl minus 1. That's exactly the dense evolution equation. Okay? So this is a function, epsilon is fixed, let's say, and z here, you integrate over. So let's assume you're in a case where you can actually decode, right? So if you can decode, then this is exactly what we had written on beforehand. This means that this is the original, what the original value was of the erasure probability. This is the erasure probability after one iteration. Now, if you can decode, this means this must always be smaller than this, right? So this thing is positive. So you have a positive function. Rho prime is also a positive function. So this means you're integrating a positive function from 0 to x, right? So if you do that, if you integrate a positive function, then it means that this function is actually increasing, right? So this is simply now plotting u of x as a function of x for different epsilons. So this is the larger, this is the smallest epsilon, larger epsilon, larger epsilon, larger. So it's clear that the BP threshold is characterized in terms of this function, right, by exactly the largest epsilon, such that these curves here are always increasing, right? Because this is always increasing, and as long as this thing here is positive, this whole thing will be increasing. So you can see that for various epsilons here, this is increasing, and at that point it just starts to flatten out, and that's exactly what characterizes the BP threshold, right? That's the BP threshold. Okay, but what's nice is that this function also characterizes the map threshold, and the map threshold is exactly that value of epsilon, such that this potential is always, so that the minimum that you look, you see there's a minimum here at 0, but that the minimum that you have here, okay, so there's another minimum here, that this minimum must be larger than the minimum that you have here. So this must be the global minimum. Okay, and that's the characterization of it. Now, so, you know, that's kind of slightly less clear, right? And in particular, it's not so clear why, as a potential function, you should pick this function. This kind of makes a lot of sense. You know, what is really the potential function, right? The potential function is, you want a function such that when you take the derivative, right, you want to see these fixed point equations in here, right? And in particular, if you look at the stationary points, the minimizers of the potential function, you want to find the fixed points of dense evolution. So that's okay, right? If that a minimum here, right? If you take the derivative here, this will happen exactly when you know, if you take the derivative, basically just the integral goes away, and you will see here exactly dense evolution, right? And so if you take the derivative and set it to 0, this will happen exactly when the dense evolution equations are fulfilled, right? So that makes a lot of sense. What's not so clear is, you know, what kind of integrating factor you should pick in here, and it just turns out that that's the nice integrating factor you should put in here. That needs, you know, a little bit more explaining why that is the right notion to do. But point is that this gives an equivalent characterization. So if you look at, so I said already, it's wherever this is positive. And what you can see from here, that this gives an equivalent characterization. So you can integrate this out explicitly. And when you explicitly integrate it out, you will see that this condition, that this is equal to 0, is exactly the same condition as this. Okay, so these two characterizations are all the same. They give all the same. They all give the same descriptions. And now, how does the proof go here with the potential function? Essentially, what you show is that, so this is the potential function for the uncoupled system. And what you now show is that there's a potential function for the coupled system. Okay, so this is now an integral in n dimensions because you have n points. And if you pick the right notation, so if you pick exactly the right potential function that you have here, so what is now the potential function of the coupled system, right? So for the coupled system, again, you're looking for a fixed point of this dense evolution, right? And these are the ones that characterize the decoding behavior. And so what turns out is that if you pick the right notion, so what do you want? You want that at the fixed point that characterizes the behavior, if you take the derivative, right? So if you take the gradient, of course, there must be that no matter where you're going, you must be in a local, at least in a local minimum, right? And so if you pick that particular potential function, and in particular you walk in a certain direction, so meaning you walk in space now, not arbitrarily, but you walk in space by moving the whole fixed point a little bit to the right. So remember, you have this decoding curve, and you walk a little bit to the right. Then you can show that in this direction, the derivative in this direction is exactly equal to this space to this height. Okay, so the derivative going in this direction is exactly equal to the height. So it means if this height is not equal to 0, then you cannot be at the minimum. Okay, and so the only way you can be at the minimum is if at the fixed point where you get stuck is if this thing here must be actually equal to 0. And as long as you're above, you know that you cannot be in a fixed point. And so hence you must actually decode. Okay, so again, I don't think in these 2 minutes I can do justice to things. But you know, if you look at Henry's papers, they're actually quite nice, and this is currently the nicest description of this phenomenon. Okay, so I think that brings me to the end. You know, each of these approaches has some advantages. If you know exit curves, then it's trivial to apply it. This tells you what's the connection to the map threshold, which this doesn't tell you. And this is kind of the easiest proof if you actually ever want to get into it. Then I recommend that you read Henry's papers. And I think that's the easier way to see why this threshold saturation works. Okay, I think that brings me to the end. Right now, I only talked about coding, okay? But spatial coupling has a priori not really anything to do with coding. Okay, so as I said, for example, for compressive sensing, there's some very nice papers by this physicist that I mentioned before, and then Andrea Montanari proves that for compressive sensing, if you use the right compressive sensing matrices and a version of BP, which they call approximate message passing, you can get information theoretic optimum compressive sensing recovery. Okay, so you can do with the minimum amount of redundancy and have an efficient algorithm that actually gets you there. And so the proof actually at the end boils down to something very similar to this potential function approach. And you can use this for other graphical models too. So for example, if you look at what's called constraint satisfaction problems, like something like KSAT, random KSAT, you can use spatial coupling to give better lower bounds on thresholds. And that's quite a different story from what I've told you here. So whenever you have control of the graphical model, then I think that's a viable option, trying to come up with something that has this structure, because it performs very well on the iterative message passing, on the message passing. If you don't have control, of course, on the measuring matrix or the graph or the code or whatever, then of course your problem that you have may or may not have the structure, and then you may or may not be able to. Okay, and that brings me to the end of what I want to say. Okay, thanks.
Of course, we do have, let me switch on the light. So instead of making you wait for actually being on time, let me give you your
I should get his because he was late.
Yeah. Well,
Thank you very much.
thanks for giving the talk. Any questions for Professor Urbanke?
Slide talking about the
Sorry, this slide talking about? Sorry.
3D decoding?
3D.
Window decoding.
Oh, window decoding, yes. Okay, sorry. Yes.
slide from the slides shows performance of window lengths.
Right.
How to select the window lengths?
So the window length, remember there's always this connection width, right? The width of the connections that you're doing, right? So right now, in what I talked about, I always assume you just connect to the nearest neighbor, okay? Had a very specific, but in general, you can pick a window in which you can do the connections, right? You agree? So you should pick it a couple times, maybe 3 times the connection width in order to have small loss.
What's the difference between for large one?
What is the difference for the connection width?
There's a window length larger.
If you make it larger, the complexity, right? So if you, okay, so what is the difference? Maybe I can show it here. So if you do it without that, your decoding complexity is of order m times l squared, okay? So versus if you do it with, then it's m times the window squared times l. But the length could be whatever, 100, right? But the window length might only be 5 or 6. So it's just it depends on, right? Because what's the point? The point is that when you have this wave, everything is happening only within a window where the wave, you could see. Remember still the decoding wave that you had coming in, right? All the decoding action is happening only where the wave is moving. There's some part which is completely constant, nothing, and there's part which is already decoded. There's no point of doing message passing there. Okay, the only thing that matters is where the window length is. Clear? So the whole point is you should only decode where actually there's some things that are changing. You should not decode. There's no point of running, updating messages that will not update because there's nothing new.
Airflow occurs -4.
So this has to do with how you do the window. Think this is maybe 4. So 4 is simply. I guess 4 is simply for this case too small in here, and that has a lot to do with how you do the the windows, the window set, right? But if you do it the right way, and these are larger ones, but it's this W8 or something, then you should not see any error for it.
And it's solutions. You want to go away, want to get a performance, minus.
Yeah, that's not a problem. For these codes, actually, airflow is.
This airflow is too high.
Yes, but that, nobody tells you to pick that parameter, right? So just pick another one, right?
I have 2 questions. The first is there any difference between LTPC convolutional codes and convolutional LTPC codes? And the second question is, if we delete the L-1 check nodes to remove the root loss penalty, how would this affect the BP threshold?
So, okay, let me answer the second one first. So you're saying if at the end, the right-hand side, I remove some of the which node do you remove?
We delete the L-1 check nodes
right.
on the right boundary.
It doesn't affect the airflow, but okay, it might affect. It doesn't affect the threshold. Okay, but you probably have to be careful. If you really want to get everything back, right, then it must be that if you really want to be at capacity, right, and let's assume you have the BC, it must be that every check node you have exactly is used once and the right way, right? And so there's no, there cannot be any loss, there cannot be redundancy, it can't be two check nodes that determine the same bit and so on, right? So if you really want to get to capacity, then you have to be careful that the system might tend to become, again, very prone to small little variations, right? So, it might happen that there's a little bit some trade-off between, let's say, error floors that you have, for example, right? So there can be things happening. So you have to be careful how to do it. And I'm not claiming that that's the best way to do it. There are many ways to do it, and I think that's a nice open problem how to do it, right? But this is just to say that you can gain something, right? So there's something you can get back, and then now you have to check that this doesn't cause you other problems. Okay? Okay, now the first question, sorry, I forgot.
Is there any difference between LDPC convolutional codes and convolutional LDPC codes?
So remember this life of Brian where they had this Palestinian front for liberation and the front for Palestinian liberation, whatever. LDPC convolutional codes, and what was the other one?
The terms in the same codes?
The point is everyone uses their own terms a little bit, but there's no, I think, standard, there's no standardized thing that one thing's one and the other one. I think for everyone probably means something slightly different, but I've not seen a systematic way of how people might use the different terms. Okay, that signifies something different. Okay, so if you say convolutional LBC codes, you really mean that the connection pattern that I showed here is really by a convolution, right? So that's the only difference to the spatial couple. Just means it could be any other way, but convolution is one form of doing that. Okay.
Especially for coupled codes. Look at the computation tree for the, say, nodes that move towards the boundary versus the computation tree for the nodes to the center. They're very different, right? Because towards the boundary you have nearer frozen nodes at smaller depths than the frozen nodes for the fixed boundary. That's probably why you're freezing those faster than those with boundary. So can you say something about look at the unfrozen degree distributions of the things near the boundary. Look at the unfrozen. If that degree distribution, you use some degree distribution. Does it have anything to do with the degree distribution come up in other?
Does it have anything? Sorry.
Do the degree distribution come up in other contexts like that?
So, okay, for example, I talked about the rate loss, right? And this is related to it. So our conjecture is that the rate loss, the real rate loss you will have, okay, will have to do with, I showed you this Maxwell construction, and there was this area with the thing, and there was some light gray area on the left, okay, and I think that's at the end the rate loss that you have to do, and that has something to do with how you should initiate. Right now we just take all the variables on the left and we simply set them to 0. But you should do something much smarter, right? And that relates to this thing. But the question is exactly how should you pick them, right? So, and we don't know exactly how to optimize that, right? Which one should you pick, right? That are most helpful and so on, right? And that's related to this rate loss, because if you're smarter, yes, but we don't know. I don't have a parametric model in which I say optimize this and then you get. There's so many ways of doing it that I don't have a some parametric model then to systematically optimize.
More questions? Yes.
In non-coupled LDPC, the non-binary LDPC much improves the performance. So can we get similar effect for coupled?
I think so, and I think I've even seen some posters here. I think so. So I've seen, like for example, Costello has some papers where they look at non-binary and also those, and then you look at the same binary length and you compare. It looks like, right? So it looks also that that's true. Now the thing is that these things are very specific now. You have to really look at all the parameters and so on. So it's kind of difficult to get generic statements, but it looks like similar things might be true. Okay.
So in the interest of time, just because we have buses to catch and so on, so we, Rudy will be having lunch with us. He'll be with us for at least part of the tour. We can have questions there. All right. So let's thank Professor Urbanke again. Thank you.